So I think we can start. It's 11:35. So today is the last lecture about isogeny-based cryptography. I told you from the beginning that we will not able to cover everything about this field, of course, but the goal of this lecture, other than presenting you these hash functions, just to have an idea of an example of protocols in this field, is to leave you with some important open problems, okay? So that in case you're interested in this topic and want to work and give some contribution to one of these problems, you can then, contact me, ask me for references, and I chose the hash function that you will see really because this will make us understand why these problems are important, okay? So let us recall what we did yesterday very quickly, just with a picture. Sorry, not this one, okay? So function is built using this kind of graphs. So I remember here that every vertex is an isomorphism class of supersingular elliptic curves defined over Fp bar. Okay. Every class is labeled by the corresponding J invariance. So here, if you take one edge between these two vertices, 201 and 132 are two J invariants defined over Fp. Here P is 227. And actually, you can use, there is a very easy function on Sage as well, and it is also very easy, even by hand, to given a J invariant to compute the corresponding elliptic curve in short bias transform. So you can play with Sage for getting these two elliptic curves. And actually, also with Sage, it's easy to recover the isogeny behind that edge. It is an isogeny of degree 2, and it can be explicitly written in this way. So this is a rational map with these two components, and you can see from the first rational map that the degree is exactly 2. Okay? So again, if you have time later today to work a little bit on the exercises, and there is that last exercise to build a supersingular isogeny graph, this is kind of interesting to understand a little bit better how to construct this graph. Okay, now we want to use the supersingular isogeny graph to define a hash function. So I go back to the paper we are referring to, so in case you want to read the details. So we said that this is the first isogeny-based protocol using supersingular elliptic curves and in particular supersingular isogeny graphs. And very quickly, we recall what is an hash function, okay? You said this, you saw this already very in detail together with Peter in its course at the beginning. So what is an hash function? For us, it is a map between, in this case, we fix our input. It has length n, okay? And we map it to another string of n bits, okay? And we require that this function has three important properties. You remember which one? Which one? Yeah, actually here, the first one is that it is fast to compute, okay? And then that is collision resistant. It means, I remember, that it is computationally hard to find two different inputs that have the same image, okay? And it is pre-image resistant. It means that if I give you an element here in the codomain, it is hard to find an element in the domain whose image is that given element. Yes?
Whether we should restrict the size of the domain?
Sorry?
Whether we should restrict the domain of a hash function, that n bit you are restricting.
So I'm taking a fixed, yeah. In this case, yes, I fix, because then you will see why. In this case, yes, it's more particular, okay? Thank you. Okay, so this is the properties that we ask for this hash function. And So I'm going now to the board a little bit, and then later we will go back to the slides for the last part of this course. So, okay. Oh. Okay, what we're going to do, we're going to fix two primes, L and P, okay? The hash function is proposed with a generic L, but we are going to work in an easier context when L is equal to 2, okay? And our P is a prime, you have to imagine, in the application, prime of 256 bits, or at least this is what they proposed in this paper. And also we require another thing, is that P is congruent to 1 modulo 12, okay? This is an important condition for like their construction, because in this case, you have that if you remember at some point we did two examples of curves, of supersingular elliptic curves, that they were supersingular depending on their modular class modulo 3 and modulo 4. Okay? And basically, under this condition, neither of the two curves are supersingular. And those two curves have the particular J invariants 0 and 728, which we do not like that much. So for this condition, 0 and 1728 are not supersingular J invariant. Okay, so that means that our graph is very nice because it is L plus 1 regular, so in this case 3 regular. 3 regular graph. Okay, and moreover, we saw that yesterday we have an exact number of vertices. It is in this case P over 12. Of course, we have to take the integer part, vertices. Okay, so this is an example. I produced this with Sage Math, so it is you know, we could draw this better. So again, here always we work with 193, which is 1 modulo 12, and actually here all our vertices. We have 169. But you know, where you find this Z2, it means J invariant which is not defined over SP. Okay, and you see here it is completely regular. If you count every number of edges from a vertex, you get 3. Okay, there are no exceptions, no particular situation. So we like to work with this. Okay, now what is the idea of this hash function? The idea is the following. So you remember, we are going to take as input a string of a fixed number of bits, so n, and we want to return a string of m bits. So the idea is the following one. This n is going to be the length of our work in the graph. Basically, we fix in the graph a starting point, a starting curve, okay? And we're going to take walks of n steps, okay? So in some way, we have to translate this string. Here we will have 0, 1, 0, 0, etc. Okay? We have to translate this bit in a path in the graph, okay? With some conventional way. And what will be our output? Well, we're going to land on a particular vertex, and the J invariant of that vertex, basically we translate it in like in binary strings, and that is the output of our hash function, okay? So the idea is the following one: translate the input into we call it non-backtracking walk of length n in the graph, in the supersingular isogeny graph GP2. So what is this length? Basically, it is an isogeny, no? Every step is an isogeny of degree 2, and we are composing then n times. So basically here, it has, we are translating the input into an isogeny of degree 2 to the n. Okay? And the output is the J invariant that, of course, then we have to translate in a sequence of bits, is the J invariance of the endpoint of the walk. Okay? So we translate this sequence of bits into a walk, and we take the endpoint. Of course, in order this to be a nice hash function, we want that we don't let in a very specific subset of here. We want that we basically cover every element in our codomain, okay? So in some sense that we cover all our J invariants by doing this construction when we, take random walks. And this is guaranteed by the Ramanujan property of our graph. So the Ramanujan property, so because the supersingular isogeny graph are Ramanujan, the output approximates the uniform distribution. The output approximates the uniform distribution. Okay, any questions so far?
Where do we start from? Like, given the input, you have to show wrong. What is the starting point of the work?
You fix a curve, so you fix one. Okay, the idea is you fix one. In the description there is no given curve, but the idea is that you can fix. If you are able to construct them, you fix one and you start from there. Yes. Okay. But then we will see that this is actually the problem of this protocol, because we are not able to fix a random vertex. I will tell you later, okay? Let's now understand how this hash function is constructed. So as just we said, we have to fix a starting curve, okay? So we fix a starting curve. Let me call E. Okay? Now I will do a drawing that really will make you clear what's happening here. So I fix my curve here, E here. Okay? How many edges do I have from that curve? 3. Okay? I denote this E0, E1, and E2. okay? Well, somehow here, you know, my first bit, it is 0 or 1, okay? So basically, our first step cannot be all of them. So in this tree that we are going to construct, we are not going to consider this branch, okay? And then how many edges do I have from E0? 2, because this one is the third edge, okay? And I can name this curve E00, E01, right? And again here, I will have 2 edges, so E0, E10, E11, okay? And so on. How will be now the 2 curves? How I can name in a way that I can understand like what's happening here? E010, E011, okay? And so on. We are not able to build, this can be an infinite graph. You know, if we take an infinite walk, we can build an infinite tree, which has always 2 like leaves starting from like the parent, okay? Sorry? Well, yes, okay, so important, exactly. That is why we don't take backtracking walks. We want a way so that we do not go back. We don't like this. So we always keep going, and the next curve will never be the previous one. Okay? Unless there are loops, okay? So you have to find in a, okay? Sorry? You can always keep going. No. You will not be stuck in some place because the graph is connected. Okay? Yeah. You can always at some point. Well, you mean if you have something like this, right? If you have something where here you have to go back. Well, I think that the graphs are chosen so that this situation cannot be, well, not completely sure, but you have to select your prime in a very, careful way. Yes?
My question was, is there any general way to cancel the point?
Yeah, because we're going to see how we're going to select, every time, because we have to give an ordering here. Every time we need a curve 0 and curve 1. So we are going to check this. Okay? Okay, so, yes. Well, for primes congruent to 1 modulo 12, sometimes you have loops. So I don't know exactly, how it works in that case. You would just, repeat your curve. But maybe if this was a good option, this hash function, they would choose a specific P so that you can work without loops and without particular cases, okay? But in general, you can add them. So in that case, you will go, it is not considered a backtracking walk because for us, this is going back. You will go just again to that curve, okay? But there are so many vertices with that loops that, is a very specific case. Okay, and I recall you, so here again, I can name this is my isogeny phi0. This is my isogeny phi1, and all these edges are isogenies of degree 2, right? So let us understand how can we construct isogeny of degree 2. It's something that I did yesterday in general, so now I think you will understand better because we work in a very concrete case with L equal 2. So imagine you have an elliptic curve defined like this. Of course, super singular, but this doesn't change what we are going to write here. And now you have an isogeny phi from E to E prime of degree 2. yesterday that when here we have a prime, this is actually a separable isogeny of degree 2. So in particular, the kernel, how is this kernel? Is a subgroup of which order? The order equal to the degree, right? 2. So it's a subgroup of order 2, and actually not just from the elliptic curve, but actually is a subgroup of the 2 torsion group. Okay? So I have to look for points in the 2 torsion group. And I remember that by doing the exercise, did you find how the points here, how are these points? So they are the points with coordinate, y coordinate 0, so I can write them like x0, such that x cubed plus ax plus b equals 0. Okay, so they are the root, the x coordinate are the root of this polynomial, union, the point at infinity. Okay? So basically, what are the possibilities for my kernel? So every point is of order 2, right? Apart the point at infinity. So all the kernels are generated by just one point of order 2. So this means points of order 2, where I remove, of course, the point at infinity because this is order 1. Okay? Yeah, this would have been nice to keep, but maybe we'll. Okay. So what does it mean, this? So as groups, we have that, okay, remember, this is a surjective homomorphism, right? And for which we know the kernel, okay? So if we talk about groups, we have the isomorphism theorem, right? Which tells us, so as groups, that E prime, so the image of that group homomorphism, is isomorphic to E over this subgroup. Okay? Why I have to specify as groups? Are they isomorphic as elliptic curves? Not necessarily as elliptic curves, because they may have different J invariant, right? So not necessarily as elliptic curves. So what happens here? So when I take my isogeny, basically this can be seen as a 2-to-1 map, because every point Q and every point Q plus P will go to the same element, phi of Q, right? Because P is in the kernel, so these elements are on the same, go to the same element. Okay. So you can see that this as a class. Okay. So now we have to do the first step. So we have our curve here, E, and we have 3 possible isogenies. So here we have E0, E1, and E2. Okay? Every one here is an isogeny. Every edge here is an isogeny of degree 2. So every isogeny here corresponds to a subgroup generated by a point of order 2. Okay? And we know exactly the shape of these points. They are x0, 0, x1, 0, x2, 0, where these x-coordinates are the root of the polynomial x3 plus ax plus b. It means that these factors as x minus x0, x0, x minus x1, x minus x2. And you agree with me that I can find an ordering for this x-coordinate with some convention, okay? I can say that, x0 is less than x1, which is less than x2, okay? Some ordering. Okay. Well, so now basically we know what to do for the first step, no? If you think about, we have to factor this. So we find x0, x1, x2. And then, given the first bit, we will select phi0, phi1, and we have to construct it by using these points. Okay? So the question here is, how can we construct an isogeny given a point? And for that, it is very useful. This can be done in Sage very easily. We have these formulas, which are called value formulas. And this is the particular case of isogeny of degree 2. So what do you have? You have your elliptic curve given in short bias transform. You have both your point of order 2, alpha 0. And these values formulas are explicit formulas for the isogeny, which has kernel that point. Okay? You see here, everything is very explicit. We have our maps, which is in terms of alpha, A, actually there are just alpha and A, and the curve, the codomain, can be written in short bias transform. Okay? So if you know this coordinate, you basically can write down by hand your explicit isogeny and your and the image of your isogeny. Okay? Whatever field. Okay? This is general. Okay? Maybe I think more in general over K, I guess. Okay? So these formulas, you can find them more in general in this paper. And actually, you have formulas for building isogenies with any kernel, okay? This kernel is just to be a finite subgroup of the set of points of your curve, okay? And they have something that look like this, okay? Well, then you can transform these into rational functions. So here you can see in the formula that you have, these formulas can be written using the points in your finite subgroup, okay? But what is nice is that in our case, this is very easy. Any questions so far? Okay, I can keep it here if you want. Okay, now we know how to compute the first step. Done. Let's see how to keep going. So imagine that we selected our first bit is 0, okay? So here basically we have to compute phi naught, phi 0. So we are computing an isogeny from E to E0 that we denote phi 0. And for what we said before, you know, in the two torsion subgroup we had 4 points. The point at infinity, P0, P1, and P2. Okay? These are all points of our starting elliptic curve. Okay? What happens? Remember that this is isomorphic to E quotiented by this subgroup. So basically here, you agree with me that these 2 points, where they will go? I'm quotienting by the subgroup, so the identity of E0, right? And here you have to keep in mind that P2 is P1 plus, P1 plus P0, okay? Because this is a subgroup. So even these 2 points will go to a same point that is phi 0 of P1, for instance. Okay? Now, it is easy to check that this new point is a 2 torsion point of the new curve E0. So, can be an exercise. This is a 2 torsion point, different from the identity. Okay? It's a 2 torsion point of E0. So what does it mean? That this is also of the shape x2 tilde 0 for some root of, you know, here this elliptic curve will be, I don't know, x cubed plus a prime x plus b prime, okay? So basically this, this is a root of that polynomial. So we have that these factors are x minus x0 tilde, x minus x1 tilde, and x minus x2 tilde, okay? So why we need to know this one? Because I told you that here after this, how many edges? 2, okay? One goes to E00 and one goes to E01, okay? But actually the vertices, the edges are 3, so where is the other one? The other goes back here, okay? It's the dual isogeny, what we denoted yesterday, phi 0 hat, okay? And actually, this isogeny here is that goes back is the one that is defined by this point, okay? So phi 0 hat, I don't know how to write phi 0. So phi 0 hat corresponds here to the kernel, well, x2 tilde 0, okay, by this point. So basically, this means if we want to keep going, we should avoid this point. So now we should take the root of the other root of our polynomial, okay? So this, we don't have to consider this. So we have to find the root of this polynomial divided by x minus this x coordinate. Any questions? Okay. This is the construction. Every time, basically, we look for 2 torsion points. We avoid the point that brings us back, and we keep going, selecting the right x coordinate compare with respect to some ordering. And we keep going. We do our work. And because of the property of the graph, this walk brings us anywhere in the graph. Okay, so this is the construction. Any question about the construction? Well, of course, you know, this requires time to understand and everything, but at least we saw like that concretely, if I was giving you an exercise, we could construct this hash function. So now we are going to understand, no, because we propose an hash function, we want to understand what it means for this hash function to be collision resistant and pre-image resistant. Okay, so I'm going to erase all this. Sorry for the confusion, but kind of complicated to write this clearly. But now let us focus on the problem, because the construction you can always study by yourself, but the problems here are important. So what does it mean? We want to understand what does it mean to finding collision in the CGL hash function. Finding collisions in the CGL hash function. Okay? So I start from a given curve, E, and I have my output here, E prime, okay? You can see as elliptic curve or as J invariance, okay, is equivalent. What does it mean to have here a collision? So what does it mean to have two different inputs that map to the same output? Every input is a walk. So basically here, I'm having two different walks that brings to the same output, okay? So finding collision in the CGL hash function is equivalent to find an elliptic curve E prime and two distinct isogenies of degree, which degree for our construction? I recall you, every isogeny is of length n, and every step has degree 2. When you compose, you multiply the degree. So 2 to the n, right? 2 degree to the n, so let's call them phi 1 from E to E prime, and phi 2 from E to E prime. Okay? So basically you have something like this. I want to do this picture here. So you have E prime, you have one isogeny phi 1 and another isogeny phi 2. Okay? But I told you that for every isogeny, there is an isogeny that goes in the other direction. This is the dual. Okay? So let me write it like this. Okay? Phi 2 dual. I also have phi 1 dual, okay? So what happens if I now compose phi 1 with phi 2 dual? What do I get? What is an isogeny that goes to itself? How it's called? Endomorphism. So this isogeny is an endomorphism of which degree? Well, I compose the 2 degree, so 2 to the n to 2 to the n, 2 to the 2n, okay, of degree 2 to the 2n. And we, you know, like, these two isogenies are different. You cannot fully understand this, I guess, but what is important is that this endomorphism is actually different. You know, we're not taking phi2 and phi2 composed with phi2 bar, which gives us the multiplication by 2 to the n map. So we are taking here different isogenies. So here we are sure that this is what is called a non-trivial endomorphism. So it's different from 2 to the n, 2 to the n, sorry, multiplication by map. So this is the multiplication, if you want to write multiplication by 2 to the n, multiplication by 2 to the n. Okay? So basically we're saying that funding collision is equivalent to find these two distinct isogenies. But also, for what we have said here, we are saying that it is equivalent to find an endomorphism let's call it alpha from E to E of degree, let me write non-trivial endomorphism of degree 2 to the 2n. Okay, this is with respect to collisions. What about pre-image resistance? So the hash function is pre-image resistant, is pre-image resistant if and only if okay. Our input, our starting curve is E. Our output, imagine that we know the output, so E prime. What does it mean to be pre-image resistant? It has to be hard to find an input that gives that output. So it has to be hard to find the isogeny, okay? So the hash function is pre-image resistant if and only if, given E and E prime, it is computationally hard to compute an isogeny phi from E to E prime of degree 2 to the n, okay? So this is our problem. And at the beginning I told you isogeny-based cryptography is based on the problem of giving two elliptic curves to compute an isogeny between them, okay? Here we have some additional information because we know the degree of the isogeny. Okay, so this is all I wanted to write on the board. So now, even though you, at some point, you didn't follow something, come back because I want to explain you now the main two problems given, all we've seen now. Any question about this? It is clear at least, what it means to find collision and to find a pre-image. Basically, it is here computing path, walks, okay, in the graph. Okay, so we are in 2018 when this paper was published on ePrint, but I think these ideas were a little bit, were starting in 2012, or at least this is what the author said in this paper. So this paper, Hard and Easy Problems for Supersingular Isogeny Graphs by Christophe Petit and Christine Lotter, okay? They prove in this paper the two following things. That for a randomly chosen starting point J0 is a J invariant, okay? You can consider a supersingular elliptic curve. The hash function is pre-image and collision resistant. This means a good hash function. The endomorphism ring problem is hard. I didn't tell you until now what is the endomorphism ring problem, but we heard already about endomorphism. So I'm going to explain you after this slide what is that. And they prove also that the hash function is not collision resistant, so it is not good when the starting, sorry, here there is a mistake, the starting supersingular elliptic curve has known endomorphism ring. So if we know the endomorphism ring of the starting curve, that hash function is not good because it's not collision resistant. Okay, so now I'm sure you wonder what is the endomorphism ring. So let me quickly introduce, a little bit, because this is very important in the field of isogeny-based cryptography. Well, the endomorphism ring, first of all, is a set. We put in this set all the endomorphism, so all the isogenies from a curve to itself, together with the zeromorphism. And it is called a ring because actually we can define two operations on this set. So the first one is given two endomorphisms. So these are maps, okay? These are isogenies. I can define a sum. I take my point P, and I send it in the point given by the image of alpha P and beta P. What is, in your opinion, this addition here? The addition on the elliptic curve, right? And now, what is nice about endomorphism, because this you can do also with isogenies from between two same curves, okay? But what is nice about endomorphism is that you can also compose them, because I can do alpha and then do beta, okay? So this composition sends the point P in alpha compose beta P. And you can prove that with respect to these two operations, this is actually a ring, okay? It verifies all the properties. And we call it an endomorphism ring. Let me do a very easy example. The multiplication by n map. We did, for instance, the case 2, okay? When you send P in P plus P. And in general, you can take an integer n, and you send the point P in P plus P plus P n times, okay? Well, because our curve, it has an addition law, this is actually an endomorphism, because it can also be written with rational function, which is called scalar endomorphism. So for every elliptic curve, you have this easy map, the multiplication by n. So these endomorphisms are known, and basically, we know everything about this, and we know that they will always be in our endomorphism ring. Okay, so for what we said, actually, and it is easy to show that the endomorphism ring is a free module, so you can find a basis, and this module contains the ring of integers through some embedding, okay? So more specifically, and this is what it is interesting for us, so the case of supersingular elliptic curves, what is the supersingular endomorphism ring? So the endomorphism ring of a supersingular elliptic curve. So if we have a supersingular elliptic curve that we can always take over fp squared, Now, I'm going to tell you some words that probably you don't know, but the endomorphism ring is isomorphic to O, which is a maximal order in the quaternion algebra BP infinity. Now, I don't, this is something else that, you can study by yourself if you're interested. We're not going to say what is a quaternion algebra, but what it is interesting for us is that this order is a Z-lattice. You work with lattices, so you know what is that. Basically, it is a Z modulo full rank. Here the rank is 4, which contains Z. And so it is generated by a basis, 1, because it contains Z, alpha, beta, and gamma, where alpha, beta, and gamma, they are 3 endomorphisms. Okay? Okay, so sorry. Okay, sorry. Okay, this is what is the endomorphism ring, and you have to know that at this time, now we are unable to produce a supersingular elliptic curve with unknown endomorphism ring. So if we construct, imagine P like very large, okay? If we are able to construct a supersingular elliptic curve over that finite fields, automatically we know information about the endomorphism ring, since all the known construction gives information about this. So for this reason, and for what Christophe Petit and Christine Lothar show, this means that at the moment, okay, this hash function is broken. It doesn't work, because they told us that if you are able to compute the endomorphism ring, then automatically the hash function is not collision resistant, okay? But because we are not able to solve this problem. So what are 2 important problems this gives us the idea for 2 important problems in isogeny-based cryptography. So the first one is the following one. It is called the supersingular endomorphism ring problem, which basically is, I give you a supersingular elliptic curve defined over fp square. The problem is to compute the endomorphism ring. So what does it mean for what we've just said? It means find a basis, so 4 endomorphisms, alpha, beta, gamma, delta, and you can always take one of them equal to 1, that generate it as a Z modular as a lattice, okay? So this is the supersingular ring problem. The complexity of this problem, is, before that, this problem is very important in isogeny-based cryptography, because you remember this problem, the supersingular isogeny finding problem that we brought in the first day, which was the problem of, I give you 2 supersingular elliptic curves, you want to find an isogeny, okay? This is not trivial to show, but this problem is equivalent to the problem of computing the endomorphism ring of a curve, So if I'm able to compute both endomorphism ring of E1 and E2, I'm able to, I can.
That is a very
isogeny, and specifically in the context where we are with the protocols that are maybe the most studied nowadays, you will hear about the During correspondence. So this During correspondence is a correspondence between 2 different words. I'm not going to be very precise. In one word, we have supersingular elliptic curve. In the other word, we have this quaternion algebra that we did not define, but you can think about them as algebraic objects associated to, that comes out when we work with supersingle elliptic curves. So quaternion algebra. And the idea is, well, this is not going to be exactly a correspondence one-to-one, but for our intuition, if I have a supersingular elliptic curve, here I have, in this size, a maximal order, for what I told you, maximal order. Of my quaternion algebra BP infinity. Okay, here my elliptic curve is defined over FP squared. And our isogenies here, so here phi, an isogeny, in this other word, translates into an ideal. Okay? Oh, quaternion algebra, they are non-commutative algebraic objects, so we have to talk about left and right ideal. But this is just for giving you a little bit an idea. Okay? And the degree of this isogeny, so the degree of phi, in this other word, will be the norm of the ideal. Okay? So just for giving you an idea why these two problems are equivalent, and again, there are lots of math behind that, is that, remember, the supersingle isogeny problem is given E and E prime, you want to find an isogeny here. Okay? Now let us go to the other word. In this other word, we have two maximal order, O and O prime. Okay? And here the problem is to compute what is called an ideal, I, which is it's called a connecting ideal. And what is important here is that given these two maximal order, this problem is easy. So it can be done in polynomial time. And what is actually also easy, it is to recover from this. Recovering the isogeny is also easy. Okay? So, if we have these two maximal orders, we can compute the ideal, and from the ideal we can recover the isogeny. But what it is difficult here? The problem which is difficult is this one. To associate to an elliptic curve this maximal order in the quaternion algebra. This is exactly the supersingular endomorphism, the computation of the endomorphism ring of the elliptic curve E. Okay? So basically, if we are able to do this problem, if we are able to solve this problem, we are automatically able also to solve the problem of computing an isogeny. Sorry? Well, it is some integer that you can associate to an ideal. It is defined with respect to the element of the ideal. Now, we are not going to do all the theory about this because we don't have time, but when, you can easily find a definition, and in algebraic number theory, any book, you can define that. Sorry? Connecting ideal, again, there is a lot of, we should recall too many things, I don't have time here. But again, I can give you references for this, okay? Well, so these two problems are now equivalent, so you can move to one to another in polynomial time, okay? And here I will give you two references where this has been proved, okay? The last like result about this basically tells you that there are no conditions here for this problem to be equivalent. If you are interested also to what I've done in this field, I actually worked very recently on this topic. Well, before that, just to tell you about the complexity of this problem at the moment. Here tilde, it means that actually you have to multiply here inside by logarithmic factor, okay? But basically the complexity is square root of p, which is exponential in the size of p, in logarithm of p, okay? So this is the current state of the art is this one with assuming GRH, the generalized Riemann hypothesis, but then it's too technical. Keep this as a complexity. And what I've done in this context, together with some other researchers, so this is a paper that we put in a print on 2023, computing supersingular endomorphism rings using inseparable endomorphism. So in this work, we described the algorithms for, I give you a supersingular elliptic curve, return to me a representation of the endomorphism ring, okay? So I really work in this field, so I wanted just to tell you for information. And the other important problem is, you remember before we said that if we are able to compute the endomorphism ring of our starting curve, then the hash function is not collision resistant. Okay? So the problem here is, and again, it is a very, it's a problem that is being studied nowadays, is give me random examples of supersingular elliptic curves for which I don't know, I don't have any information about the endomorphism ring. Because I told you that all the constructions, so we have construction for supersingular elliptic curve. One construction is I take a supersingular isogeny graph, I start from a curve, and by exploring the supersingular isogeny graph, I can build all the supersingular elliptic curves, okay? But since I always know, the starting, the problem is that when I start from a curve, actually I know the endomorphism ring, and by doing PAF, I actually translate my information on the endomorphism ring to the other curves, okay? So this is one construction. Other construction uses complex multiplication theory, and again, we have information about the endomorphism ring. So if you are able to solve this problem, to tell me for P of cryptographic size, this is a random supersingular J invariant, this is actually a very important problem at the moment, because actually would make the CGL function, hash function, a collision resistant and also pre-image resistant hash function, okay? Well, this is about these two important problems, and I told you that, of course, in this short course of 6 hours of isogeny-based cryptography, I wasn't able to tell you a lot about other isogeny-based protocols, but let me say something else about this, just for knowledge. So the CGL hash function was proposed in 2006, okay? Then I remember you that in 2010, there was that paper that was telling that if you use ordinary elliptic curves, you have a sub-exponential attacks. Okay. So in 2011, Zhao and DeFeo, they write in their abstract, our work is motivated by the recent development of a sub-exponential time quantum algorithm for constructing isogenies between ordinary elliptic curves, okay? So they propose, so in 2011, SIDH, sometimes it's good to know what there is behind the acronyms. So SIDH, Zhao and DeFeo. And this means supersingular, isogeny, Diffie-Hellman. Okay? So Diffie-Hellman, this means that it is a key exchange which is based on supersingular isogeny graph. Based on supersingular isogeny graph. Okay, I want to give you an idea of about how this works. So actually here we have to use, we fix a prime of a particular form, P of a particular form. And we use two different primes, L equal 2 or 3, okay? Because we are going to work both in the in the supersingular 2 isogeny graph and the supersingular 3 isogeny graph, okay? Remember, in a Diffie-Hellman key exchange, we basically have Alice and Bob that want to find a secret, a common secret, okay? So I would need some colors here, but let's try to understand without colors. I put myself on one vertex of my supersingular isogeny graph. Let me call it E0, okay? And then the idea is that Alice and Bob, they start doing random walks on this isogeny graph. For instance, Alice will take, so let's say that Alice, she walks on the 2 isogeny graph, 2P, GP2, and Bob walks on the 3 isogeny graph. Okay? So Alice starts, she walks, and she lands, she does a walk of a specific length. So this is an isogeny of a degree, let's say 2 to the EA, okay? And so phi A 2 to the A isogeny. And she lands on an elliptic curve EA, okay? And then Bob does the same thing, but now he will work on the 3 isogeny graph. So, okay, we'll walk on the 3 isogeny graph. It means that it's going to compute an isogeny phi B of 2 to the 3 to the EB degree. So it will arrive on some curves EB. And well, the idea is now Alice is here. And Bob is here. Well, both vertices are both vertices of the 2 supersingular isogeny graph and the 3 supersingular isogeny graph. Imagine that they exchange position because basically they are exchanging this information. So now Bob is here and Alice is here. Okay? Question is, can they perform some walks in a way to arrive to the same vertex at the end? And no, Joe and DeFeo, they proved that this is possible. So basically here, Alice will will compute her isogeny on the 2 isogeny graph, and Bob will do the same, okay, in the 3 isogeny graph, okay? And they will arrive to some common vertex, and this is the key at the end, okay? Well, this problem, you know, from outside, for reaching this common secret, the isogeny are not enough for arriving there, but they need also to publish here some additional information, which are the images or some points. Okay. Well, I'm not going into detail, but imagine that other two EA and EB, they will publish the images of 2 points with respect to the isogeny. And actually, this additional information was the reason why, very recently in 2022, sorry, I forgot to put the reference here, Kastrick, Decroux, Maino, Martindale, and Robert, they found a polynomial attack to this problem, okay? So, you know, in isogeny, we were very proud of this because it reached the 4th round of the NIST submission, but actually, very soon later, they made this attack, polynomial attack, that uses very complicated mathematics, abelian surfaces, and other things of algebraic geometry. And so, now it is completely insecure, okay? Well, there are other key exchange which are based also on a supersingular elliptic curve. This is called the Seaside, 2018, which use also supersingular elliptic curves, but now with a different ideas. Basically, they use the ideas proposed by Couvain, Rostov, Seves, Stolbunov with ordinary elliptic curves. But because of this, it is also not very good because we have quantum, here I should say quantum sub-exponential attacks also in this case. So still, it is something which is very efficient, but not like the best in terms of security. So, and of course there are many other protocols, so where we should focus our attention, or at least where the community is probably focusing our attention, other to the problems that I've already told you about, it is on this new scheme, SCI, okay, compass post-quantum signatures from quaternions and isogenies. You see here the word quaternions, which is a digital signature scheme proposed in 2020, which has been just submitted, so in 2023, to the NIST call for post-quantum digital signatures. Well, this protocol is very complicated to explain you because actually it uses what I raised, the word of quaternion algebra. So in order to understand how this works, you should learn about quaternion algebra, maximal orders, connecting ideal. So if you want to have an idea of all those things that you were asking, you can go to the background section of this paper, for instance, for finding some references. Okay? So this is basically the last proposition about in isogeny-based cryptography, where, like, I think the community is focusing their attention, and for sure, you know, there will be, I hope there will be new proposal and new things. So with this, more or less, I ended whatever I wanted to say, but I want to say like something for concluding. So you can see that isogeny-based cryptography is a field where several things have been proposed, several things have been broken, but where also we have still some very interesting mathematical problems. Okay? So if you are interested into the mathematics behind that, I told you about 2 mathematical problems that you can work, on which you can work about. And maybe one of you can be one of the future can be one of the future researchers in this field working on some of these topics. And I also want to say that I'm really thankful for this opportunity of giving this course about isogeny-based cryptography. I want to thank Elisa because really giving me this opportunity was super nice, and all the organization team about, you know, for this CIMPA School. you were like great, spent a wonderful time in Pondicherry, and I want to say thank you to all of you because you were like amazing, like always there asking questions during exercises, and this implication in research is very important, and this is what will really make you a successful person in life, whatever you want to do. So for this, I ended a little bit early. Sorry about that, but thank you very much. And of course, I'm taking the last questions about. Sorry?
Like a summary of that paper,
No. This was in the public key. Okay? So in the public key, you had both the J invariance of these two elliptic curves, and you have also the information about like the images of two particular points of the starting curve. Okay? Either by phi A and phi B. And the attack really relies on this information and on the degree of the curve. Okay? Well, you have to go in dimension 2 with a billion surfaces. You consider products of elliptic curves and you do the construction there. Maybe I will go back to my country, I will give you all the references, maybe for isogenies, depending on which field you want to work on. Yes. Is it? No, it is not commutative. Quaternion algebras are not commutative algebraic objects. Well, the module, well, doesn't mean that when you multiply, is commutative as with respect to addition, but not with respect to composition. No. Okay, right? Yeah, and it is not commutative only for supersingular elliptic curve. For ordinary elliptic curve, it is commutative, and there are field-based exponential algorithms for computing it. Okay, I think
no more questions, no more comments. So let's thank Anna again.
Thank you.